Okay. Hello. I think I'm audible and sorry for the delay. Am I audible? If anyone, okay. I think I'm audible. So sorry for the delay and I'll try to continue 10 more minutes at the end of the class so that it will adjust. So this is the second tutorial of the measure and integration course. This is measure and integrations. Okay. So now in the last class we have just started with the definition of sigma algebras and all these things, and so now uh, in this second tutorial we will try to solve some problems which will be mostly relevant to the assignment 2 basically. So let me just find a problem. Actually, I have the problem. So I will today is also not able to write those problem in. I mean, not able to take picture of those problems. So I will also write problems and solve that. And from the next class, I will try to take picture and try to paste here so that it will be better to visualize. Okay. So first problem is that let S be a sigma ring. Let S be a sigma ring of uh, subsets of a non-empty set X. Okay, and this is X, and let mu is not a mu be a measure actually. Mu S be the sigma ring. Sigma ring means this is closed under union and and the or closed under countable union, not only union but countable union, and it's closed under the differences. It is ring and sigma ring. Okay, so let mu be a measure, and measure means mu be a measure, and measure means it is non-negative and zero at the empty set, and the it is countable additive on the disjoint countable union. It is additive. Okay, let I equals to 1 to infinity be a measure of sets in S. Define uh, limit infimum n tends to. We are defining limit infimum of this sets, measurable sets, not measurable. This sets in the sigma ring. Okay, En is equals to union n equals to 1 to infinity, intersection I equals to n to infinity En. So this is first, and second is that limit. We are defining this, or limit supremum of n tends to infinity En, that is equals to intersection n equals to 1 to infinity and union I equals to n to infinity ei. This is actually ei, this is not en. So now the first question is that of sub question, this is the mu of limit infimum n tends to infinity En. This is less than equals to limit infimum n tends to infinity mu of En. This is the first question. So let's um, and the second question is that of. So second question I will do when we will do the first question, and after that we will do the second question. So let's first try to solve this one. So with the definition, we'll start with the definition. So um, just a minute. The definition. I'll use the definition to prove this one. So mu of, we have to use some. You have to use the properties of mu, that is the countable subadditive, the countable additive decision additive that I have to use, and then we'll be able to solve. So give me 1 minute. It's a few seconds actually, not 1 minute. Yeah. So here is the thing is that so first we have to prove this one, limit n tends to infinity is equals to this one. Okay. So let's for this we'll consider the some subsets for any k belongs to natural number n. Let bk is equals to union of n greater than equals to k and ek. Okay, and we'll denote ck. We'll denote. Okay, let's start with that denote first ck. So let ck is equals to intersection of n greater than equals to k and ek en. This is the intersection en. So basically, you can look at you can write it here actually n equals to k to infinity basically. So I'm writing this one as ck. So then what we got actually from here we can say that ck actually is subset of ck plus 1 because this is the smaller one. So if we increase k, this will number of intersecting elements will be low, so that less. So therefore, ck is subset of ck plus 1. Okay. So now ck is subset of ck plus 1, and so this is then ck ck equals to 1 to infinity is an this is an increasing sequence. This is an increasing sequence, and this is an increasing sequence. And then what we can say is that we know by and if mu is a measure, so what we can say mu is a measure, then this is so there is a theorem that is discussed in the class that I'll state that is continuous from the if mu is a measure on a sigma ring, then this is continuous from the below, I think. Yeah, that will be needed here. So it is known that we use result if mu is a measure on a sigma ring, in fact any on ring in fact, so sigma ring of then mu is continuous from below. That says if ei are as sequence of sets in the sigma ring and ei are increasing sequence, then limit n tends to infinity union of ei is equals to or en, that is sorry this will be measure of then measure of union of ei I equals to 1 to infinity, this is equals to limit n tends to infinity mu of en. So this is the case. So if we use this result, so what we get here, ck is an increasing sequence and mu is a measure on the sigma algebra. So therefore ck and this ck are countable intersection. So if it is sigma algebra, so if it is sigma ring, then it is closed under countable intersection as well. Okay. So if it is sigma ring, then it is closed under countable intersection as well. So ck is also elements in the sigma ring. What is the sigma ring? It is denoted at S. So therefore, this is an increasing sequence. So therefore, we can write the measure of union of k equals to 1 to infinity e ck, that is equals to, one can write that limit k tends to infinity mu of ck. So that means mu of union of here it is given union of n equals to 1 to infinity, n equals to 1 to infinity, or k equals to 1 to infinity, intersection I equals to n to infinity e I. This is equals to limit n tends to infinity mu of this cn basically. Okay, so now second fact is that this but but note that this Cn is equals to, that is intersection of all I greater than equals to n. So that means this is subset of particularly En and subset of Cn. So mu of Cn, that is less than equals to mu of En, as if E and F both are in sigma algebra, sigma ring S, and mu is a measure on that, and with the and E is subset of F, then mu of E is less than equals to mu of F. So with this property, we can write this one. So therefore, what we are getting here actually, that mu of limit in limit infimum, I think, limit infimum En here, limit infimum En tends to infinity. This one, limit n tends to infinity, E is limit infimum n tends to infinity En is equals to mu of union of n equals to 1 to infinity intersection I equals to I greater than equals to n e I, that is equals to, that is what it is, that will be less than equals to limit n tends to infinity mu of en. And I think this is what we are asked to prove. Okay, so as this is true for all n tends to infinity, as this is true for all n tends to infinity, so therefore this will be less than equals to and this is already less than equals to limit n tends to infinity limit infimum. Okay, sorry, this is limit infimum or limit supremum. So let me check a little bit. Use en and limit. Okay, but this is actually exactly equals to the limit infimum. Okay, so here is the thing actually. So let me write in more precise. So this is equals to limit n tends to infinity mu of cn. Okay, mu of cn, which is equals to limit n tends to infinity, which is equals to limit n tends to infinity infimum, because this is the exactly limit, so therefore this will be same with this one. So this is equals to limit infimum, and we know that mu of cn is actually less than equals to mu of en. Okay, so therefore limit infimum will also be the preserve that similar equality. So this is less than equals to limit infimum mu of en. So this is the thing. So this completes the proof. Okay. So another thing is that with that definition, so I'll prove another there is another equality which is involving the limit supremum. Okay. So I'll prove that one. So let me find the question again. Yeah. So the second question is that under the same question B, second question says that if here you need the finiteness, because finiteness, without finiteness we can't prove that to the, if for some n belongs to natural number, we have mu of union I equals to n to infinity ei. This is finite. Okay, and then mu of limit n tends to infinity supremum of en, that is greater than equals to limit n tends to infinity limit supremum n tends to infinity mu of en. So here actually why these are needed actually, that I'll discuss, because in the, if you note that in the last proof, that is the limit infimum, there we have used the fact that we have used what is called bounded below, bounded continuity from the below. So here I will use the continuity from above. But for continuity from above, we need only this finiteness is needed. Without that, we can't use the continuity from above theorem. Okay. So for that purposes, we have to use this one. And again recall what is limit supremum. So what is limit supremum? So limit supremum n tends to infinity, the set En, this was actually equals to, this is actually equals to, by definition this actually equals to intersection n equals to 1 to infinity, union I equals to, union I equals to n to infinity, and ei, this is the thing. Okay. So we here is also will consider. So let's consider an. An is equals to union I equals to n to infinity e I. Okay, this is the first thing. So therefore, what we can get is that limit n tends to infinity, limit supremum n tends to infinity, e n is equals to intersection n equals to 1 to infinity mu e n. Okay, a n. So here one can note that here we will use the fact. So now it is known that mu of intersection n equals to 1 to infinity a n is equals to limit n tends to infinity a n. Here there is the mini theorem. Here we have these two facts. One is that it is given that mu of a n is finite for some n, obviously for some n, we don't need for all, for some n belongs to natural number. First fact. Second fact is that mu is continuous from above. Mu is continuous from above. What that says, if ei are a decreasing sequence or sequence of elements in not in subsets, sequence of sets, sequence of subsets, one can write subsets in a ring. Actually, here we need the sigma ring, because here we have sigma ring, that's why it is happening. Without, I mean, just if we take ring, then some facts will not be hold, because this here considering a n as the union of some elements. But if we want to, here it is given that ai are the element in the ring S, but S is also sigma ring, that's why the countable additivity will be there. Okay, so that's why this ai are also, so from here one can say that this ai also in the sigma ring S for all I belongs to natural number. Okay, so that's why there, and this here, if I consider ai as the if ai are sequence of subsets in a ring, here only this theorem is for ring only. Ring are of subsets of a non-empty set, subsets of a non-empty set, non-empty sets X, then and a mu of an is finite for some n, then mu of intersection an, that is equals to limit n tends to infinity an. So we have to use this one. So that's why I am using that one. Okay. Now similarly, we'll use the similar type of argument for the as we have given for the previous one, so that we get the um, so that we'll get the desired result, which is what we are looking for. Okay, so therefore what we can get is this is equals to, oh, this is will be the mu of en, which is I'm making mistake, mu of en. Okay, but here we can look at an is actually, an actually what is that, that is actually union of I equals to n to infinity ei. So in particular an is actually superset of en for all n belongs to natural number. Okay, so therefore mu of en, that will be less than equals to mu of an. Okay, now what we got actually, mu of limit supremum n tends to infinity en, that is equals to mu of, that is equals to mu of union of n equals to 1 to infinity an, that is equals to, sorry, this is intersection. This is intersection, that is equals to limit n tends to infinity an, okay, and that is equals to limit, here we need supremum, okay, limit supremum, because this is the exact limit exists. So limit supremum n an, but as we have mu of an, but as mu of an is greater than equals to mu of en, so if we take the limit supremum on both sides, it will preserve the equality. Limit supremum in mu of en. So I think this is what we are looking through for the. This is it. So I'll do another problem. Okay, so we'll do some other problem. So, but now the next problem, I will try to leave some problems and. Okay, so here is a problem that is need to be little descriptively written. So let's me write that one. So I will not start problems on Lebesgue, what is called the Lebesgue measure. That I will do on the next one. So we today only discuss only the general one, and in the next one we'll discuss the Lebesgue one. So because there will not be, in fact, there will not be problem because the assignment 3 submission date is obviously beyond of that date, so that will not create any problem. So. mm So, okay. So another problem is that let H be a hereditary, let H be hereditary sigma ring of subsets of a non-empty set X, and let mu star be an outer measure on H if E and F are two elements in H, and and if at least one of them is Mr. measurable, so that mu star E mu star F is equals to mu star A union F plus mu star E union F mu star E intersection A. Okay. So okay, we start this one. Okay, so let's do this one. So just a minute. Okay, so here it is said that it is asked to prove okay, so it is asked to prove that mu star E plus mu star F equals to this one you have to prove. Okay, so no, question is that let H be a hereditary sigma ring. So hereditary sigma ring means this if a set is there, then all its subset will be also be there. Okay, sigma ring of subsets of the non-empty set X and um, non-empty set X and mu star be outer measure of on H and E and F are at least one of them are measurable. This is one fact. This is the fact. At least one of them are mu star measurable. So recall that what is mu star measurable? We call a set E, for example, SE belongs to the H is called is mu star measurable or is mu star measurable if for any A belongs to H, mu star of A is equals to mu star of A intersection E plus mu star of A intersection E complementary. So this is the two condition. So if mu star measurable, this is the condition, and but this is equivalent to the fact that actually greater than equals to, because less than equals to is always there. Less than equals to is always there, so that's why less than equals to is always there. So that's why it is um, that's why it is always the greater than equals to is enough. Okay, so we are here. So therefore, if A is set to measurable if for any A belongs to this subset. So let's first assume that that let's take E is measurable. So here it is saying that at least one of them is Mr. measurable. So let E is Mr. measurable. Okay, Mr. measurable. Now, okay, one I will avoid one fact that if mu star E, if one of them, this mu star E and mu star F, okay, so here I can write that separately. If mu star E or mu star F are infinite, then the equality holds. Then there is nothing to prove over here. Then 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 the equality holds. then the equality holds, because if E, for example, if E is if mu star E is infinite, so in that case, so here it is infinite. If mu star E, or if one of them are not finite, if one of them are not finite, then the equality holds. For example, mu star E is infinite. If mu star E is infinite, as E is subset of E intersection F, so therefore mu star E will be less than equals to mu star of E union E intersection. Sorry, here, as E is subset of union F, as E is subset of E union F, so therefore mu star of E will be less than equals to mu star of E union F. Okay. So, but if E mu star is infinite, then mu star E union F will be infinite, and in that case, this will be infinite. So right hand side will be infinite, and here mu star is infinite. So left hand side is also infinite. Similarly, if mu star F is infinite, so in that case one can write that F is actually subset of E union F, and similarly mu star F is infinite, and this is again infinite. So then we'll have the problem. So this is what we'll call the trivial case. So this is not trivial case. So this is in the equality holds, because this is the very, I mean, easily one can prove. But let's assume that E is measurable. So there, that means what we can and 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 uh, and mu star E and mu star A both are finite. Because if one of them are finite, then infinite, then we have proved that case. And if mu star E and mu star A both are finite, then their intersection will be measure of the intersection mu star E intersection F, that will again be finite, and mu star E union F, that will be again finite because of the subadditivity property. Okay, so we'll consider these two are the finite, and we are assuming that E star is finite measurable. Okay, okay. So in that case, mu star E union F, that is equals to mu star. Here we have written E is measurable, so we can write E union F intersection E plus mu star E union F intersection E complementary. This is by definition, completely by, not by definition of the measurability. Okay, definition of the mu star measurable. Okay, so now if we consider this one E union F and intersection E, so that will be again E. Okay, and the right hand side E union F and intersection E complementary, so then it will be so let's keep this one right now. Okay, so this, let's, so here it is the E union F and intersection E complementary. Whatever the region will be, that is this one, that means this will be, okay, so one can write this one, this F and E complementary. So here you can write, actually here you need to give this bracket actually. So here you can write here E union F intersection E complementary. This means E intersection E complementary union of F intersection E complementary. So that, but this is equals to empty set and union of F intersection E complementary. So basically we'll get F intersection E complementary. So this is can be, this is there. So that means we'll get mu of F intersection E complementary. This is first thing we got here. Okay. So now, and also recall that mu star of F here by definition of the, and again, and here we have obtained mu star of E union F by the definition of the measurability of a F E. So here we will obtain the mu star of F using the definition of measurability of E. So that means F intersection E plus mu star F intersection E complementary. Okay. So but mu star of F intersection E that I got here, that is equals to mu star no, that is union. Okay, E union F we got. So here is the intersection. So so we'll get mu star of E intersection F. So we get union. We want to obtain the intersection of F, that is equals to mu star F minus mu star F intersection. So we can write it here, minus, uh, because both of them are finite, so that's why you can, this subtraction you can do. Okay, so mu star F intersection E complementary. Okay, so now F intersection E complementary. So now, okay, so I think we are ready now. So now let's calculate mu star of E union F plus mu star of E intersection F, that is equals to what we'll get. First fact is that mu star E plus mu star F intersection E complementary plus mu star of F minus mu star of F intersection E complementary. This will be cancelled out because they are finite. So I will get mu star of E plus of mu star of F. So this completes the proof. Okay. Now we'll go to another problem. So this completes the proof. So let's write another problem. Um, so problem number 3. Problem. So we prove this one. Okay, so here is the problem, but problem is little long. So let me write this one. So let x be a, let mu be a measure. Let me be measure on a sigma ring. That means this is closed under countable union and differences of subsets of a non-empty set X. Let mu bar be the induced measure. I'll recall what is induced measure. Induced measure defined on measure defined on S bar. S bar is the set of all measurable sets basically. I will say what is measurable. That is written the sigma ring of mu star measurable sets. Let A and B, two element in S, be such that mu of B sub minus A is equals to 0. If A is subset of E and that is subset of B, so that E belongs to S closure. S closure is the so okay. Mu is a measure on a sigma ring S. It is given. First fact. Okay. Second fact is that mu bar is the induced measure defined on S bar. Okay. So what is S bar? The sigma ring of mu star measurable sets. So here, first of all, mu is the measure it is given. So we will consider. Uh, so here is the let let sigma ring generated, or S is the sigma ring that is given, and mu is the measure. So first we have to give what is the mu star measure. What is mu star actually here? Mu star is actually same with mu on S. It will be same. Okay. So now here is first is first we have to consider let R J V. Okay. So here first we okay, but we'll just recall some facts. So what is the recalling that recalling the facts that um, okay, so we are recalling the facts that suppose we are given S is the sigma ring. Okay, that's okay. But if first we have to consider the hereditary sigma ring is the this is hereditary sigma ring, hereditary sigma ring generated by S, generated by S. This is the first fact. Next is that the mu star of any element for any E belongs to this hereditary sigma ring HS, mu star E is equals to, so in particular this is contain generated by X means that always contains the S. Okay, so now mu star E is equals to infimum of summation of mu star of EI such that this E is actually covered by this union of EI, where union of EI where I equals to 1 to infinity such that EI is coming from the sigma ring S. So this is the mu star me, that is the outer measure. Okay, so this is the outer measure. Outer measure. Okay, now with this outer measure, so with this outer measure, S bar equals to collection of all those sets E belongs to S such that E is measurable with respect to measurable with respect to the outer measure, respect to the outer measure mu star. So this is yes, this is actually S bar. So this is measurable means that mu of for any set A belongs to H S, mu of A is equals to mu of A intersection E plus mu star A intersection E plus mu star A intersection E complement. That is what it will turns out to be the S bar. So and now if we restrict and then it is known that mu star of E is equals to mu star of mu of E, for all E belongs to S only, not in HS. If E is coming from HS, then does not guarantee this one. So that's why it is only for E belongs to S only. That is that is mu star is actually extension of mu on hs. Okay, so now similarly, or one can similarly, if I consider so now if I just restrict in mu star, and this is the extension, so now restrict mu. Now restrict mu star. So mu bar of some set uh, element A is equals to mu star of A, where A is coming from S bar. So basically we have outer measure, and if we with this outer measure we'll consider all measurable sets, and after that, that will be sigma measurable again. That will be sigma measurable. Okay, this is coming from HS basically. HS, that will be sigma measurable. So what we are getting, actually we have an sigma ring S, okay, and we will consider the hereditary sigma ring generated by S, and we will consider the outer measure, and we will consider the measurable sets in HS, and that will be the S closure, that will be S bar denoted by, and that is the sigma, that is the measurable sets basically, that is the all measurable, and we measurable sets in HS, and we restrict the outer measure mu star on A. So that is this is what mu. Okay, these are the sort of actually recalling. Okay, so now we have to go to our problem. So now what is the, these are the all fact recalling. The mu bar be the induced measurable measure defined on A. So what is mu bar, that is clear, and the sigma ring of mu star measurable sets. This is the sigma ring of mu star measurable sets. Let A and B, two element in S, be such that B mu of B minus A is equals to 0. This is given. Okay. So now if A subset of E subset of B, then show that E is actually measurable. That is what I have to prove. Okay. This is what I have to prove. So basically we have to prove that. So we have to prove that. Okay, these are the fact already given. Given that mu of B subset of A is equals to 0, right? And mu of and A subset of E subset of B, then show that, then we need to show that, then we need to show that E is actually measurable. That is, we need to show that mu star of A is equals to mu star of, this is not A, we have to give some another set notation, F is equals to A intersection or F intersection A plus mu of F intersection A complementary for all A belongs to H of S. This is what we have to, sorry, for all F belongs to H of S, and this is E. We have to prove that E complementary for all F belongs to F. Okay, this is the thing. So how I will prove that? So let's take, note that E is equals to A union E minus A. Okay, that I can write because E is actually containing A, so E can be written this, and these are the disjoint union. This is disjoint union basically. Okay, but here it is as A is subset of E subset of B, so this E minus A, this is subset of B minus A, because just we can look at the diagram. Suppose this is A, this is E, and this is B. this is E, and this is A. So therefore E minus A, this is the region, this one, that obviously B minus A, that is the full region, that that is, and also this is clear from E minus E subset of B, that will also be true. So now, also it is given that mu of, okay, first of all from here we can write mu of this means mu, in fact, star E, uh, mu star or mu of okay, it is given that mu of, I think, B minus C, mu of B minus A is equals to 0, as B minus A belongs to the sigma algebra S, which is already inside the S closure. That implies that mu bar of B minus A, that is equals to 0, but as S closure is a sigma algebra, sorry, S closure is the hereditary sigma algebra, X closure is in hereditary sigma. Here is the hereditary using hereditary. S closure is the exclusive, as exclusion is the collection of mu star measurable function, measurable sets in hereditary sigma algebra, hereditary in HS. That is, I can, in short, I am writing HS. That implies B minus A is again in S bar. Okay, this is the fact. Okay, I think I have to prove B minus A, E belongs to S closure. Okay, that is I have to prove. B minus A is in, sorry, B minus, sorry, that implies for any subsets of B minus A is in S closure. Is in S closure. So in particular E minus A, that is in S closure. First of all, in particular E minus A, that is in S closure. Now A is in S, so that's why this is in S closure. That implies A union E minus A, that will again be in S closure. That implies E is in S closure. So this settles the problem. Okay. So this is the problem. So E belongs to S. This is the problem we have to prove. Okay. Now, let's look at another problem. So let's do another problem, and Okay, so this is a little different. So let's write this on problem number 4. Let X be a non-empty set, and H is the full collection, power set collection. Okay, let mu I star for I equals to 1 and 2 be two finite outer measure on H. Let Si bar 1 and 2 be the respective measurable sets if mu star, now we are defining mu star equals to mu1 star mu2 star, so that mu star is an outer measure, mu star is an outer measure, and that the class of mu star measurable set, class of mu star measurable sets S1 bar intersection S2 bar. Okay, this is full stop. So this is what is the problem. So problem says that suppose we have a non-empty set and we are considering the H is the collection of H is actually the full power set, and considering that mu1 star and mu2 star are the two finite outer measure on H. So obviously H is the um, H is power set. So this will be hereditary, because every set subsets is there, so therefore this will be hereditary, and what is called the hereditary sigma algebra, countable union, and everything will be there because every subset is there. So that's why this is hereditary sigma algebra. Actually, sigma algebra. This is not only the sigma ring, hereditary sigma ring, but this is hereditary sigma algebra, because full set that X is also there. Now considering two measure mu1 star and mu2 star, they are two outer measure, and corresponding to that two outer measure, we are considering the collection of all measurable sets. Okay, so collection of measurable sets with respect to that outer measure, and if we take the new outer measure mu star is equals to mu1 star and mu2 star, then question is what are the measurable sets with respect to that outer measure. Okay, first we have to show that mu star is an outer measure. Okay, that we have to, so then that is nothing special. So mu star is outer measure, that is clear more or less. Mu star is outer measure. First of all, that mu star of some set A is equals to mu1 star A plus mu2 star A, that is greater than equals to 0. The as mu1 star comma mu2 star are outer measure. This is for all A belongs to the power set X, because we are given the, this is what is called the power set X, and that is actually equals to the H. Okay, so and the second thing is that empty set will be 0, mu star empty is equals to 0, and the subadditivity that mu star of some union AI, or one can write union of I equals to 1 to infinity, that is equals to mu1 star union of I equals to 1 to infinity AI plus mu2 star union of I equals to 1 to yes. Okay, so there is an internet disruption, so So this will be mu star of union of I equals to 1 to infinity ai, and you can write this is less than equals to limit this is less than equals to 1 can I equals to 1 to infinity mu 1 star a1 ai plus I equals to 1 to infinity mu 2 star ai, and that is equals to summation of I equals to 1 to infinity mu star ai. So this is all. So mu star is outer measurable, that is very much clear. Now the main fact is that uh, what are the measurable sets. So basically we have to show that outer measurable with respect to outer measure. So mu star measurable outer measure, and that is so that mu star is outer measure. This is done. Second is that the class of the mu star measurable set is S1 star S2 star. So it is we have to prove that mu star measurable set with respect to this S bar is equals to S bar is the collection of mu star measurable sets. Yeah. Collection of mu star measurable sets, that is equals to S1 bar in intersection S2 bar need to prove. This is what you have to prove. Okay. So that means if a set is measurable with respect to this new measure new, then that will be measurable outer measurable with respect to older one. So let E belongs to S bar, that is for any set A belongs to this power set, we can write mu star A is equals to mu star A intersection E plus mu star A intersection E complementary. That is equals to mu1 star A intersection E plus mu2 star A intersection E plus mu1 star A intersection E complementary plus mu2 star A intersection E complementary. Now if I take these two terms, mu1 star this and mu1 star that, so we'll get this one is equals to mu1 star of A plus if I take these two terms, so we'll get mu2 star of A. Okay, so yeah, okay. Okay, so no, I'm not writing this one. So this is what we have. So now fact is that what I have to prove is that A is measurable with respect to question is contained, or that means what, and also this mu star A is equals to by definition mu1 star A plus mu2 star A. Okay, so that means what we can say is that mu1 star A minus mu1 star A intersection E minus mu1 star A intersection E complementary, that is exactly equals to mu2 star A intersection E, or one can write that is equals to minus of mu2 star A minus, now one can write this is equals to minus of mu2 star A minus mu2 star A intersection E minus mu2 star A intersection E complementary. Okay, so therefore but note that here is the fact which is making sense. Okay, so note that mu2 star, note that in general mu1 star a is actually less than equals to mu1 star a intersection e minus mu1 star a intersection e complementary. Okay, so therefore, and the similar thing holds for for mu2 as well. Mu2 star a intersection e minus mu2 star a intersection e complementary. Okay, so therefore, what we can say here is that uh, this is actually negative, right? And second term is also negative, but we have minus, so therefore this is greater than 0. So that means this term, but these two are equal, so that implies, so 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 therefore they have to be equals to 0, because a term is both, I mean, if I take that is equals to lambda, so that is equals to lambda is equals to these two terms. Okay, take, so I'll write here only, say this is equals to lambda, this implies, let's, this is equals to lambda, say, okay, we are taking this is lambda, so that means therefore lambda equals to 0, that implies mu1 star a is equals to mu1 star a intersection e, or a intersection e, plus mu1 star a intersection e complementary. Second is that mu2 star a is equals to mu2 star a intersection e plus mu2 star a intersection e complementary. That implies that e is belongs to s1 bar, and this implies that E is belongs to S2 bar. So this implies that E is belongs to S1 bar intersection S2 bar. So we have started that E belongs to S, and that implies S bar is subset of S1 bar intersection S2 bar. So conversely, if I take E belongs to S1 bar intersection S2 bar, that implies for any A belongs to the age which is actually power set, we can write mu1 star A is equals to mu1 star A intersection E plus mu1 star A intersection E complementary. Similarly, mu2 star belongs to A is equals to mu2 star A intersection E plus mu2 star A intersection E complementary, because A is in S1 bar and S2 bar both simultaneously. So now adding these two, we will get mu1 star A plus mu2 star A equals to mu1 star A intersection E plus mu2 star A intersection E plus mu1 star A intersection E complementary plus mu2 star A intersection E complementary. That implies mu1 star A this is says that this is mu star A intersection E, and the second one says that this is the first term. This is the first term that mu star A intersection E, and this is the second term that says this is the mu star A intersection E complementary, and also this is equals to mu star A. That implies that A is in measurable with respect to the outer measure mu. So that says that S1 intersection S2 bar is subset of S bar. That implies S bar is equals to S1 bar intersection S2 bar. Okay. So this is this is another problem. So let's go to another problem. Number 20. So let's write another problem. What it says, let E is an subset of R, real number subset. E is said to have an infinite codimensional, infinite infinite condensation condensation point if E has if E has uh, if E has uncountably many if E has uncountably many. Yeah, this is the very known fact from the uncountably many points outside every every interval every finite interval. Okay, so E is said to be infinite condensation point. E is said to be have an infinite condensation point. E has uncountably many points outside every finite intervals. E has uncountably many points outside every finite intervals. And let H is equals to P of R, that is power set of, that means the collection of all subsets. Define for a measure, we want to give give a measure. Define E for a subset of R. Define an outer measure mu star E is equals to 0 if E is empty or finite or countable. Finite or countable. Main point is the discrete sets. That means this can be integer, rational numbers, or finite set is there, and any finite set. And 1 if E is uncountable but without a finite condensation point, but without an infinite condensation point, but without an infinite condensation point, and the infinity if E has has an infinite condensation point. Infinite condensation point. Okay, so this is the new story. So let's again, and before going to the problem, I'll just understand what it is given. So, so E subset of R, and E is said to have an infinite condensation point if it has uncountable many points outside of every finite interval. That means if we take E is a set and take intersection with any finite interval, so this will have so I mean basically E minus any finite interval if I take, then it will have the infinite number of points. That is what uncountable number of points, not only infinite, uncountable. E has uncountable many points for outside every finite interval. That means for any a less than b and a b r belongs to real number. For any a b belongs to real number and a less than b, e minus close interval a b, that has to be uncountable many points. Okay, so this is the, and we have given the measure is that it will be 0 if it is discrete set, if it is uncountable discrete or countable, then, and if it is uncountable, it is 1, but it should not have any infinite condensation point, and infinity if it is an infinite condensation point. Okay, so the questions are, so that first is that mu star is an outer measure. Mu star is a sigma finite outer measure. Okay, on H. Second question is that the only mu star measurable set are at most countable sets or their complements. And the third one is that the induced measure mu bar is not sigma finite. So here three facts is that mu star is an in sigma finite outer measure. Okay, on H first, and second is that the only mu star measurable sets that are at most countable sets that are either countable or their complements. So that means uncountable sets are not mu star measurable, and the induced representation mu bar is not sigma finite. Okay, so that mu bar is obviously on the measurable sets here. Okay, so this is not sigma finite. This is the question. Okay, so we look at one by one. Okay, so first question is sigma finite outer measure on H. Okay, so the outer measure is clear. Okay, outer measure is clear, but sigma finite thing we have to prove. So let's take a set. Okay, we have to prove that for every set there exists an countable collection of subsets whose union is actually which covers the set E, and each of them are of finite measure. This is what. Okay. So for E can be written E intersection R, which can be written E intersection minus N2 N plus 1. I think minus N2 minus N plus 1. Okay, that is in the other way. Okay, N to N plus 1 basically. N to N plus 1. This is the, so one side I'll take close and one side is open. So let's take left hand close and this is open. And N belongs to integer, all integer. Okay, this is countable, there is no problem. Now, and consider, so intersection, okay, this is I'm making a little mistake. Intersection union of n belongs to integer z, n goes to n plus 1. So that is equals to union of n belongs to Z, E intersection n goes to n plus 1. So now note that these are the set which will denote by En. Okay, so that means this is equals to union of n belongs to Z En, where En is equals to E intersection close interval n plus 1. So note that here E can be, note that here E intersect En can be infinite, En can be uncountable, but 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 this fact that is said to be have infinite condensation point if E has uncountable many points outside every finite interval, but En does not have infinite condensation point. This is what the important. So that will make the measure is finite. Does not have infinite condensation point. That implies mu of En is less than equals to 1. That means either that will be 0, I mean E intersection to n plus 1, that either will be countable or finite or an empty or finite or countable, but but or it can be it is uncountable but does not have the infinite condensation point. So that implies that E is equals to union of En or E subset of En and mu of En is finite. So this gives mu is sigma finite measure. Outer measure I am not doing. Outer measure is very easy. Outer measure, just you have to use the countable subjectivity, but that is also true because you can break that way. Okay. Now the now we will go to the second one. What second one says? Second one says the only mixture measurable sets are at most countable sets or their elements. That means or their complements. So second thing is that let E belongs to power set of R or subset of R, I can write, because we are taking the sigma algebra here is the full set R. Then if E is measurable, E is mu star measurable, then for any subset A of R, we should have mu star A should be equals to mu star of A intersection E plus mu star of A intersection E complementary. Okay, this has to hold for any subset A of R. Now, um, now if E is uncountable set, so here you have to show that either E has to be countable or its complement. So by any chance, if E is uncountable set, at most countable sets or their complements. These are the things. Okay. Only mixture measurable sets are at most countable set, their complements, but their complements is also uncountable. It can be, for example, if I take finite set, complement is uncountable. So you have to give some, I mean, if a set is not countable, or let E is not countable, neither complement of a countable set, neither complement of a countable set, then is not countable, neither countable or nor uncountable. Then you have to show that we have to find a set A for which this does not hold. Okay. So if we take E is so we have to, if E is countable or uncountable. Okay. So then consider we have to find an A for which this equality does not hold. So that means we have to find an A for which one side is finite and another side is infinite. That way we have to consider. Okay. A intersection E, uh, just a minute. So A intersection E, okay, just 1 minute. If the only measurable sets, the at most countable sets are their complements. Okay, if a countable set is there, the complement will be there, but if E is not countable or not complement of a countable set, that means either E is countable, E is uncountable, or E complementary is uncountable. So in that case, that is either E is uncountable or E complementary is uncountable. Okay. Okay. So in that case, if I consider A is equals to Okay, okay. So if I consider particularly A is equals to some particular interval 0, 1, okay. So in that case, mu star of A is equals to 1 because this is uncountable set, but this does not have infinite condensation point because it does not intersect with what is the infinite condensation point that have infinite condensation point if he has uncountable many points outside every finite interval. So if I consider a finite interval, it's outside there will be infinite number of intervals. So that is not the case, and let A and B, so starting from the different way, let A and B belongs to E and A less than equals to B, not less than equals to, so this is T less than B belongs to B. Then if I consider A is equals to close interval AB, then the mu star of A is equals to 1 because this does not have infinite constant point because this does not have uncountable many points outside of any interval that does not prove for this fact. And now A intersection E, okay, this this is also this is also is equals to 1 or less than equals to 1. It can be okay. E is uncountable. Okay, E is uncountable. So that means it will intersect with. Okay, sorry, I have to keep some different argument. This argument is okay. So as E is uncountable, as E is uncountable, E or E complementary is uncountable. Countable. There exists at least one natural number n belongs to natural number such that E intersection n to n plus 1 or E intersection n to is uncountable, okay, because if for every n E intersection close close n to n plus 1 open if that is countable, then ultimately E will be countable. Okay, so but that is not the case. E is uncountable. So therefore, so at least one n will get for which E intersection close n to n plus 1 is uncountable. Okay, so this is uncountable. This is uncountable. So let's consider E is equals to A is equals to close n to n plus 1. Okay, so then mu star of A that is equals to 1 because this is not empty, not countable. So that's why this is exactly 1. And E intersection n to n plus 1 that is also uncountable. This is also uncountable, is uncountable. So that means mu of this set, mu of A, this set is also 1 because that is uncountable. Because E intersection A that is also uncountable. And another way is that mu star A intersection E complementary. Okay. Now, if uh, there is two case, if E is completely contained in A into n plus 1 there is total uncountable points. So here if we use star A intersection in complementary, what it will be? Is it possible it will be 0? Is uncountable set. Suppose we are giving is countable. Okay, this is given. Okay, so if I consider A is equals to n plus 1 in E, then A intersection E that will be equals to E, and A intersection E complementary that will be equals to A intersection E complementary that is equals to okay, so this will be okay. I will consider this is the A, then this is 1. Okay, now A intersection E complementary, that means 0 then. Union A intersection E is equals to A intersection E is equals to E. Okay, so I will consider this one in the next. It is not complete. I will consider this is in the next class. Consider in next tutorial. And I'll do now one problem and easy. So and one problem and I'll stop for today. So problem 7, I think. So let x be an uncountable set, okay, and S be the collection of at most countable sets and empty set, including, so at most countable set means that includes empty set, okay, including empty set, okay, and their complements. So that means this is actually algebra, because empty set is there and its complement is there. That means X is there. So that's what is algebra. First question, so that S is a sigma algebra. Second question, if mu is the counting measure on S, so that it is complete. Complete means I will recall the definition. So first of all, I will do these two, and after that we'll consider the later one. Okay. So first of all, that S is sigma algebra. So clearly, if a set, empty set and X both are in S. Okay. If E1, I equals to 1 to infinity, is a sequence in S, is a sequence of sets in S, then I have to prove their countable union. I equals to 1 to infinity. This is also there. So that means either um, either for each I belongs to natural number, either ei are countable, ei is countable, or complement of countable sets. Okay. So let's take A is equals to union of I belongs to some indexing set I1, where I1 is equals to where I1 is equals to all those I belongs to natural number, such that EI is countable. Okay. Second is that B is equals to union of all I belongs to I2, where I2 is equals to all those natural number, such that EI is uncountable. EI is complement of countable. EI is complement of countable set. So note that here here this I1 and I2 can be intersection can be non-empty, because there may exist a set which is countable, and that their complement is again countable. That is also possible. Okay. So that means, for example, if no, that is not possible. Sorry, this is not possible. If either EI will be countable, or if EI is subset of R, if EI is subset of R, then either it is countable, then but if a set is no, if EI is in S, then either it is countable or its complement is countable. So that means, okay, a set EI in S that can't be both countable and its complement is again countable. Can't happen. If I mean, if a set in ES is countable, then and it can't happen simultaneously that it is countable and its complement is again countable. Okay, that can't happen. Okay, so therefore I1 plus I2, I1 and I2, that is empty, and I1 union I2, that is equals to full natural number. There is no problem. So basically we have to find I belongs to natural number is equals to A union B. So to so union of I belongs to natural number, um, belongs to the set S, enough to show enough to show that A and B both are in S. Okay, but that is very easy. Clearly, A is union of countable sets. A is countable union of countable sets that implies A is countable, that implies A belongs to S. This is first place. Second place is that B is equals to union of I belongs to I2, that can be written as intersection of EI complementary, I belongs to I2, its complement, right? We can write. Now, as EI complementary for for I belongs to I2, EI complementary are countable is countable as for each I belongs to this I2, EI complementary is countable, that in the intersection is again countable, is again countable, that imply intersection of I belongs to I2, EI complementary, that is inside the set S, that implies their complement, that is again in the set S. So that implies B is in the set S, because if a set is contained in S, their complement will also be contained there, because either it will contain countable sets or complement of that set. So basically, if a set is there and its complement is there, so S contains A and B, that implies A union B is in S. Okay, and this is clear. If two set is there, then their union will also be there. This is also clear. Why that will be true? Because S is sigma ring, that is already said, I think, right? I think X be the countable set and S be the collection of at most countable sets and their complements, then show that S is a sigma algebra. So I have to show that union is there. If A is there, B is there, then their union is there. So then if A and B is there, both either countable or both are either uncountable. So in that, I mean, both either countable or their complement is countable. In that case, this will be there. If A is countable, so we can write here. Here I am writing. So only the case you have to verify that if A is countable and B complementary is countable, so then A union B is there. That I have to prove. Okay. So A union B can be written. Okay. So A union B can be written as, so two set is there, their union is also be there. I think this is very trivial that I have no time. Okay. That implies the full union is actually there. This is what our main target. Union I belongs to the natural number. This is in there. The second thing we have to show that if mu is the counting measure on S, so that it is complete. So complete measure definition, what it says, complete measure definition says that if mu of E is equals to 0 for some E belongs to S, that implies if then for any, if F subset implies F is in consider, F is in containing S, that is what I have to do. So mu is counting measure if mu is counting measure, mu is counting measure, then it is complete. Complete. So that means if it is counting measure, so then mu of e equals to 0 implies that e is actually empty set, because otherwise the counting will not be 0. So that implies that any subset of e that is only possible empty set, and that is then this F is subset of E, then F will be there. But I think there is some problem, so let me check this one, because this is very trivial, but that it is not that much trivial, I think. So the question is that mu is a counting measure so that it is complete. That complete means this is, let X be an uncountable set, okay, and this be the collection of at most countable sets, including the empty set and their complements. But this, why this is so easy, that if mu is the counting measure on S, then show that it is incomplete. So that it is complete. Complete means that if a set is there of measure 0, then any subset of that set will be there. But that is already here. It is very easy to see these things. So this is complete. So that implies that mu is complete. Okay, so this is all. Um, so I'll stop here, and next class I will start Lebesgue measure, and mostly we have to understand those things Lebesgue measure, because those things are actually will be most important. These are the general foundation. This sigma algebra, sigma ring, hereditary sigma ring. These are the foundation thing, and the Lebesgue measure will be the main thing. Okay, well, from the next class we'll consider Lebesgue measure. Thank you.